The bite angle is a geometric parameter used to classify chelating ligands in coordination chemistry, including organometallic complexes. Although the parameter can be applied generally to any chelating ligand, it is commonly applied to describe diphosphine ligands, which can adopt a wide range of chelate ring sizes. Diamines. Diamines form a wide range of coordination complexes. They typically form 5- and 6-membered chelate rings. Examples of the former include ethylene diamine and 22-bipyridine. 6-membered chelate rings are formed by 13-diaminopropane. The bite angle in such complexes is usually near 90 degrees. Longer chain diamines, which are floppy, tend not to form chelate rings. Diphosphines. Diphosphines are a class of chelating ligands that contain two phosphine groups connected by a bridge, also referred to as a backbone. The bridge, for instance, might consist of one or more methylene groups or multiple aromatic rings with heteroatoms attached. Examples of common diphosphines are DPPE, DCPM, Figure 1, and diphos, Figure 2. The structure of the backbone and the substituents attached to the phosphorus atoms influence the chemical reactivity of the diphosphine ligand in metal complexes through steric and electronic effects. Examples: steric characteristics of the diphosphine ligand that influence the regioselectivity and rate of catalysis include the pocket angle, solid angle, repulsive energy, and accessible molecular surface. Also of importance is the cone angle, which in diphosphines is defined as the average of the cone angle for the two substituents attached to the phosphorus atoms, the bisector of the PMP angle, and the angle between each MP bond. Larger cone angles usually result in faster dissociation of phosphine ligands because of steric crowding. The natural bite angle. The natural bite angle, beta N, of diphosphines, obtained using molecular mechanics calculations, is defined as the selective chelation angle, PMP bond angle, that is determined by the diphosphine ligand backbone. Figure 3. Both steric bite angle effect and the electronic bite angle effects are recognized. The steric bite angle effect involves the steric interactions between ligands or between a ligand and a substrate. The electronic bite angle effect, on the other hand, relates to the electronic changes that occur when the bite angle is modified. This effect is sensitive to the hybridization of metal orbitals. This flexibility range accounts for the different conformations of the ligand with energies slightly above the strain energy of the natural bite angle. The bite angle of a diphosphine ligand also indicates the distortion from the ideal geometry of a complex based on VSEPR models. Octahedral complexes prefer angles near 90 degrees and tetrahedral complexes near 110 degrees, since catalysts often interconvert between various geometries. The rigidity of the chelate ring can be decisive. Bidentate phosphine with a natural bite angle of 120 degrees preferentially occupy diequatorial sites in a trigonal bipyramidal complex, whereas a bidentate phosphine with a natural bite angle of 90 degrees preferentially occupy apical equatorial positions. Diphosphine ligands with bite angles of over 120 degrees are obtained using a bulky, stiff diphosphine backbones. Diphosphines of wide bite angles are used in some industrial processes. A case study: hydroformylation. The hydroformylation of alkenes to give aldehydes is an important industrial process. Almost 6 million tons of aldehydes are produced by this method annually. Rhodium complexes containing diphosphine ligands are active hydroformylation catalysts. The ratio of linear to branch to aldehyde product depends on the structure of the catalyst. 1 intermediate, RHH, alkene, CO, L2, exists in two different isomers, depending on the position of phosphine ligands. Figure 4. Diphosphine ligands such as DPPE, which has a bite angle of about 90 degrees, span the equatorial and apical positions. Isomer. Diphosphenes with larger bite angles, above 120 degrees, preferentially occupy a pair of equatorial positions. E-isomer. It is believed that the E-isomer favors formation of linear aldehydes, the desired product, in an effort to create rhodium complexes in which the phosphine ligands preferentially occupy the equatorial positions. The use of diphosphine ligands with wide bite angles such as BISBI, Figure 5, has been investigated, with a bite angle of approximately 113 degrees. BISBI spans sites on equatorial plane of the trigonal bipyrimidal intermediate complex. Figure 6. The structure of the intermediate RHH diphosphine CO2 does not, however, determine the regioselectivity of the hydroformylation. Instead, the formation of the linear versus branched aldehydes is determined upon formation of RHH diphosphine CO alkene, and the subsequent hydride migration step. During the coordination of the alkene to the intermediate complex, the effective bite angle on the regioselective formation of the linear product is explained by the steric crowding at the RH atom that results from the interactions of the bulky backbone of the ligand with substrate molecules. The large bite angle that results from the bulky backbone causes the 5-coordinate RHH diphosphine CO alkene intermediate to adopt a structure that relieves steric hindrance. Thus, BISBI occupies the equatorial positions, where it would have the most space. This preference of a transition state that relieves steric hindrance pushes the reaction toward the formation of the linear aldehyde. The regioselectivity is also controlled by the hydride migration, which is usually irreversible in the formation of linear aldehydes. A large bite angle stabilizes the intermediate in this process. However, after the addition of the alkene occurs, considerable steric congestion causes the phosphine ligand backbone to conform in such manner that the substituent attached to the alkene is moved towards the hydride. This results in the formation of more of the linear product than the branched product. Furthermore, studies using xanthose ligands with bulky backbones in hydroformylation have indicated an increase in the rate of catalysis in metal complexes that contain diphosphine ligands with larger bite angles. The electronic effect of this increase in reaction rate is uncertain, since it mainly depends on the bonding between the alkene and rhodium. Large bite angles promote alkene to rhodium electron donation, which would result in an accumulation of electron density on the rhodium atom. This increased electron density would be available for pi donation into the antibonding orbitals of other ligands, which could potentially weaken other bonds within the catalytic complex, leading to faster reactivity. The application of diphosphine ligands to catalysts is not limited to the process of hydroformylation. Hydrocyanation and hydrogenation reactions also implement phosphine-mediated catalysts. The use of diphosphine ligands in catalysis has allowed the optimization of industrial processes, and has led to the development of new catalytic systems. See also constrained geometry complex, Josephus ligands. Further reading: Klinger, R. Chen, M. Rathke, J. Kramars, K. 2007. Effect of phosphines on the thermodynamics of the cobalt-catalyzed hydroformylation system. Organometallics. 26. 2. 352. DOI 10.1021 OM 060768D